We interact with software constantly, right? I mean, every tap, every click, it's sending instructions somewhere.
Yeah, absolutely.
But have you ever stopped to really think about how those instructions, get turned into action?
That's a great question.
Today, we're going to take a journey into the heart of a language many of you might use or have definitely heard of, Ruby.
Exactly. And Ruby's famous for its elegance, isn't it? The code often looks quite clear, almost like plain English sometimes.
Mm-hmm.
But behind that simple surface, there's a pretty sophisticated engine running things.
Right.
So our mission in this deep dive is to understand that engine a bit better, specifically how your Ruby code goes from text on a screen to, well, an actual running program.
And we'll be focusing on something called YARV.
YARV, yeah. Yet another Ruby VM.
Yeah.
That's the virtual machine most Ruby implementations use today.
Okay. And to help us navigate this, we've got a really interesting article from Ruby Stack News. It's called Understanding Ruby's is YRV, Yet Another Ruby VM Stack Mechanics, From Code to Execution.
That's the one. It does a great job breaking things down.
All right, let's jump right in then. So the article points out that even the simplest bit of Ruby code, like really simple, goes through a surprisingly complex process.
Oh, definitely. Take something incredibly basic like 1 plus 2.
Well, let's do. Yeah, okay. We all know that's 3.
We do. But the way the Ruby virtual machine gets to that 3 is, well, it's fascinating. It involves this clever system using stacks and a set of lower-level instructions.
Stacks, okay. The article mentions YRV uses a dual stack system, 2 stacks. Can you maybe paint a picture for us? What are these stacks doing?
Sure. So you've got 2 main players here in YRV's stack world. First, there's what's often called the instruction stack. Sometimes people call it the internal stack or the operand stack.
Yeah.
Think of this as the VM's workbench, its immediate workspace. It's where the actual values, like numbers, are held and manipulated while these low-level instructions are running.
The workbench, I like that. And the second one?
The second one is the Ruby call stack. Now, this is managed differently, using a C structure, actually, called .rb control frame it.
Okay, a bit more technical.
A bit, yeah.
Mm.
But its job is really about managing the flow of your program. It keeps track of things like which methods are currently running or when you enter and leave blocks of code.
Okay. So if I were to try an analogy, maybe the instruction stack is like a chef's cutting board, right? Where they're actively chopping the onions, mixing things.
That works well.
And the call stack is maybe more like the main recipe book, keeping track of which major step you're on, like step 3, saute vegetables.
That's a really good way to think about it, actually. Yeah, it captures the difference quite well. The immediate work versus the overall structure.
Cool.
Now, to see this in action with our 1 plus 2 example, we need to understand something crucial. Ruby code doesn't just run directly on your computer chip.
Right. It's interpreted or compiled somehow.
It's first compiled, into a simpler intermediate set of instructions. We call this bytecode.
Bytecode, okay.
And the article actually shows us the specific bytecode YARV generates for just 1 plus 2. Looks like this.
Let me see.
Ruby VM instruction sequence.main at test.rb 0000 trace 1 1 0003 put object 1 0005 put object 2 0000 put object 2 0007 opt plus called data.mid plus a rgc.1 rgs simple 0007 opt plus called data.mid 0009 leave.
Whoa, okay. Yeah, that definitely looks less like Ruby and more like, well, machine instructions of some sort.
Exactly. It's the language the virtual machine understands.
So should we walk through this line by line, see how it uses that internal instruction stack?
Let's do it. So ignoring the first trace line for now, the first real instruction is put self.
Put self. What's happening there? Puts itself where?
Onto the instruction stack. Remember the workbench. Put self takes the current object, which in a simple script like this is just the main self object, and pushes it onto that stack.
Ah, okay. So it's like setting the stage, establishing the context.
Precisely. You need to know who is doing the adding, essentially.
Gotcha. Then we have put object 1 and put object 2. These seem a bit more obvious.
Yeah, those are pretty straightforward. Yeah. Put object 1 pushes the integer value 1 onto the top of the instruction stack.
Okay.
And put object 2 does the same for the integer value 2.
So after those two, our stack looks like bottom is self, then 1 above it, and 2 right on top.
You got it. We're loading up the numbers we want to operate on.
Makes sense. Loading the operands. Okay, next up, opt plus. That sounds promising. Opt plus, called data.mid.plus rgc.1 rgs simple. Looks like where the magic happens.
That's exactly right. Opt plus is the optimized instruction for addition. What it does is it looks at the instruction stack.
It sees a 1 and 2.
Well, it sees the top 2 items, it pops them off, First it pops the 2, then it pops the 1.
Okay, so they're off the stack now.
Temporarily.
Hmm.
It then effectively tells the object that was below them on the stack, which is the one it just popped, to perform the plus method, using the 2 as the argument.
Ah, so it's like calling 1 plus 2.
Essentially, yes, under the
Yep.
hood. And the result of that operation, which is 3, gets pushed back onto the top of the instruction stack.
Okay, clever. So it takes 2 things off, does the math, puts 1 thing back on.
Exactly. That's a very common pattern in stack-based virtual machines.
So now our stack just has self at the bottom and 3 on top.
Right.
And the very last instruction is just leave. What's its job?
Leave basically signals that we're done with this sequence of instructions. It takes the final value remaining on the top of the instruction stack, in our case, the 3, and makes that the return value of this whole chunk of code.
Wow. Okay, so even that tiny 1 plus 2 goes through this whole little dance. Push self, push 1, push 2, pop 1, add, push 3, leave with 3.
Yeah. It's quite a process.
It really is eye-opening.
Yeah.
Makes you appreciate, like you said, what's happening under the hood, even for simple stuff.
Mm-hmm.
Now, the article also talks quite a bit about the other stack, the Ruby call stack, and this derb control frame it thing. How does that fit in? We didn't seem to need it much for just 1 plus 2.
Right, for a simple expression like that, it's less prominent. But the Ruby call stack and these Ruby control frame as structures, they become absolutely crucial as soon as your code gets more complex. Think method calls or using blocks.
Okay.
Every single time you call a method in Ruby, or every time you enter a block, like with an iterator, a new frame gets created. And this frame is represented by one of these Ruby control frame as structures. It gets pushed onto the Ruby call stack.
A frame for every call or block. And
Yeah.
what's in that frame? What information does it hold?
Well, it holds several vital pieces of information, according to the article. Key things include the PC, which is the program counter.
Program counter, like where we are in the code?
Exactly. It's like a bookmark. It points to the next bytecode instruction that needs to run within that specific method or block.
Okay. What else?
Then there's the SP, the stack pointer. This is really important. It keeps track of the current top of the other stack, the instruction stack, but specifically for this frame's operations.
Ah, so each method call sort of gets its own little section of the instruction stack to work with, pointed to by its frame's SP.
You've got it. It defines the working area for that frame on the instruction stack. The frame also stores the object context for that method or block, and also a type field, which tells the VM whether this frame represents a method call or a block or maybe an evil, things like that.
So let's say I have a method foo that calls another method bar. When foo starts, a frame for foo goes on the call stack. Then when foo calls bar.
Exactly. A new frame for bar gets pushed on top of foo's frame on the Ruby call stack.
And this bar frame would have its own PC pointing to the start of bar's bytecode, and its own SP maybe pointing higher up on the instruction stack.
Precisely. And these frames are linked. There's something called the CFP, the current frame pointer, which always points to the frame that's currently executing. In this case, it would point to bar's frame.
Okay. And when bar finishes?
When bar finishes and returns, its frame is popped off the Ruby call stack. The CFP then automatically points back down to foo's frame, restoring foo's context, its PC, its SP, so foo can continue exactly where it left off.
Okay, that's actually a really neat organized system. You've got the instruction stack doing the calculations and the call stack managing the overall flow and context using these frames.
It is. It's a very standard but effective way virtual machines manage execution.
Well, let's get practical. Why should someone listening, maybe just writing, regular Ruby web apps or scripts, why should they really care about all these internal stacks and frame pointers? Does it actually help?
That is the million-dollar question, isn't it? And the article makes some good points here. While, sure, you can write perfectly good Ruby without knowing any of this, understanding these mechanics can be, well, incredibly helpful sometimes. First off, debugging.
Ah. Oh, okay. How so?
Ever seen a stack level 2 deep error?
Oh, yeah. Usually with runaway recursion or something. Yeah.
Exactly. That error is literally telling you that the Ruby call stack, the one with the Ruby control frame structures, has grown too large because you've pushed too many frames onto it without popping them off. Understanding how method calls add frames helps you pinpoint why it's happening.
Right, you can trace the calls that led to the stack getting so deep.
Precisely. And it's not just stack overflows. Sometimes you get weird behavior with blocks or procs, maybe variables not being what you expect. Understanding that blocks also create frames,
Yeah.
and how those frames capture their surrounding environment can really shed light on those tricky bugs.
That makes a lot of sense. It's like knowing a bit about how your car's engine works. You don't need to be a mechanic to drive, but if it starts making a funny noise.
Knowing what might be causing it is super useful for diagnosing the problem.
Yeah.
Same idea.
What about performance? Does knowing this help write faster, Ruby?
The article kind of hints at this. It's maybe less direct, but being aware that every method call, every block invocation has this overhead of creating and managing a frame, well, it can inform your choices.
Cool.
For instance, if you have extremely performance-sensitive code, maybe you think twice about very deep recursion, knowing it builds up that call stack. Or perhaps you might favor an iterative approach in some cases, just being mindful of that frame management cost. It's usually small, but in tight loops, it can matter.
So it gives you another factor to consider when optimizing.
A factor, yes. And beyond the purely practical, the article also suggests it leads to a deeper appreciation of Ruby.
Yeah, I can definitely see that now. It demystifies it a bit, doesn't it? You see the cleverness behind the curtain that makes the nice syntax work.
Absolutely. It changes your perspective from just using a tool to understanding the engineering behind the tool.
Hmm.
And, if you ever wanted to build developer tools yourself, like debuggers or profilers for Ruby, then this stuff, the SERP control framework, the stacks, it becomes absolutely essential knowledge.
Foundational. Okay, so for listeners who are now thinking, this is kind of cool, I want to see this myself, what can they actually do? The article mentioned a couple of ways to peek behind that curtain, right?
Yeah, this is a great starting point. You can actually see the bytecode for your own Ruby code. There's a built-in method, rubyvm.instructionsequence.com. Compile your Ruby code.desasasm.
Oh, nice. So you just put your Ruby code in the string.
Yep, replace your Ruby code with whatever snippet you're curious about, maybe a simple method or a loop, or even just 1 plus 2 again, and run that in Ruby or a script. It will print out the exact YARV bytecode instructions.
That sounds like a fun experiment. See how different Ruby constructs translate.
It's a fantastic way to learn. Try comparing the bytecode for, say, A0 versus A dot first. You'll see differences.
Cool. And what was the other path for the really adventurous?
Well, for those who really want to go deep, the article points towards the C source code of MRI Ruby itself. That's the reference implementation.
Diving into the C code? Okay.
Specifically, the file vm.c is where a lot of the core virtual machine logic lives. That's where you'll find the actual C code that manages those RB control framework structures, interprets the bytecode, handles the stack pointer, everything.
Into the engine room.
Definitely the deep end. But it's the ultimate source of truth if you want to understand every last detail.
Wow. Okay, so from a simple 1 plus 2 all the way down to the C code that actually runs it. It's quite the journey.
It really is.
So let's try and wrap this up. The big takeaway here seems to be that Ruby's lovely, readable syntax, it's actually brought to life by this quite sophisticated dual stack system inside YARV.
That's the core of it. You have that internal instruction stack, the workbench, handling the immediate calculations with bytecode.
Right, the Pute object, dot plus, leave stuff.
Exactly. And then you have the Ruby call stack using those RB control framework frames, managing the bigger picture, the flow control, method calls, block contexts.
It's a well-oiled machine, basically.
It truly is. It's a testament to the design that it can manage all that complexity while still letting us write code that feels simple and elegant.
So, for you listening, now that you've got this glimpse into Ruby's inner world, maybe it sparks a bigger thought. How might understanding these kinds of fundamental processes, even just a little, change how you think about all the technology you use?
That's a great point. It's all built on layers, isn't it?
Yeah, layers of abstraction. From the code we type, down to these virtual machines, down to the operating system, down to the hardware. It's all connected. Something to mull over, definitely.